Alright, so today we're going to talk about we're going to finish up alkenes. So this is going to be alkenes 3. This will be the third installation of alkene reactions. We're going to start with our discussion of halogenation. And we're going to talk about the addition of bromine and chlorine. Alright, so just to discuss, I'm going to cross out this here. Okay. Alright, so just a couple of aspects of this reaction. We're going to have a bridged intermediate. We are going to have, there's no regio specificity. We are adding either Br2 across the double bond or Cl2, so the same things are adding to each carbon. Alright, there is stereospecificity. Because we have a bridge, we're going to have anti-addition. Alright, so let's look at this mechanism. Step 1 is the same as all the other electrophilic additions. We're going to form a bond between the nucleophile and the electrophile. So let me draw my alkene. Okay, first step is electrophilic addition. This will result in a bridged intermediate where we have a positive charge on the bromine. Just try and redraw this for you. Okay, so this is our bridged bromonium. Alright, now, in the second step, you know what, let's do this. Let's just move down. In the second step, we're going to make a new bond between the nucleophile and an electrophile. Alright. So again, this is similar to all the other reactions that we've done. So now Br minus can come in. Now let's pause for a minute. Now it doesn't matter, there's no regioselectivity here. Okay. However, we need to consider the stereo specificity. So I said in the beginning that we have anti-addition, similar to what we have in oxymercuration. So let me redraw this so that maybe it's a little bit more clear. Alright, so that what I'm trying to show you here is that the bridge is on one face of the ring. So what will happen is when Br minus attacks, it will attack anti or from the opposite face. And we break that carbon Br bond. And what we will get is a dihaloalkane, where the bromines are trans to each other. Alright, what we need to discuss right now is that your products depend on the starting alkene. So if we have cis-2-butene and we treat it with Br2 in dichloromethane, what we will get is a pair of enantiomers. If we treat trans 2-butene with Br2, what you will find is that you will get a meso compound. I need to fix this. So if we were to do the configurations around these carbons, it would prove to you that this was a pair of enantiomers, and this is a meso compound. If we do the configuration around this carbon here, the bromine is the first priority, then we have this carbon and 3, so let's redraw this. 1, 2, 3, so this would be R, okay? And if we now do the configuration around this carbon, what you would see is that we'd have 1, 2, 3, so let's redraw this. 1, 2, 3. The highest priority group is pointing away from us. Okay, so what we would have to do is flip the whole molecule over, and when we do that, we would find that the configuration would be R. The enantiomer is SS. Here, with the trans 2-butene, the products, the configuration is SR, okay, and RS, and you can see that we have a pair of meso compounds. Alright, so let's move on to the addition of water and a halogen. This is called hydrohalogenation. When we use water as a solvent, okay, so we're going to treat an alkene with Br2 or Cl2 in the presence of water. What will happen is, instead of a Br- or a Cl- adding as a nucleophile to the positively charged intermediate, we'll have the addition of water. And then we add a net addition of OH and Br or OH and Cl to the carbon-carbon double bond. The product is called a halohydrin. Here we are going to have regioselectivity and stereoselectivity. Water will add to the more substituted carbon of the double bond. Right. These reactions all have the same mechanism. So let's go through the mechanism. The first step is to make a new bond between the nucleophile and the electrophile. Alright, so let's take the following alkene. and we are going to add Br2 in water. The first step of the reaction is electrophilic addition. We're going to form our bridge. Okay, now let's pause. Typically, when we had halogenation, Br- would then attack this positively charged intermediate. Now we have water present. Because water is in a greater concentration, than Br-, water acts as the nucleophile. Now, water will attack regioselectively. It's going to attack the more substituted carbon because this carbon bears a greater partial positive. If we were to draw the bridge in the center here, okay. We can think of the positive charge being distributed as such according to these resonance structures. This is the greatest contributor. This is the second greatest contributor. Sorry, let me draw. This is the second. And this is the last contributor. You have more positive charge here because it's the more stable carbocation. Okay, so all of the rules that govern the mechanisms of the other reactions we looked at govern this mechanism here. So that water will add to the more substituted carbon. In an anti-fashion. We generate an oxonium ion that we then have to deprotonate, and we can get our product. Okay. Again, your products will depend on your starting alkene. We need to consider, when I drew the stereochemistry, we need to consider the other substituents on the double bond. So let's go back to this intermediate. What I want you to think about is I want you to think about the carbon backbone being in the plane and the bridge above the plane. The water is going to come in and attack from below. We need to consider what might happen to the other groups attached. When the water comes in to attack from below, what we can do is we can keep the ethyl group. All right, let's just draw the carbon skeleton in the plane. All right, so that the water, if it's coming in below, it will be coming away from you, but the methyl group has to now be coming towards you. The bromine has to be anti to the OH so that this is coming out at you and the hydrogen is coming in. We can also have the enantiomer. Okay, again, let's keep that carbon chain in the plane, the longest carbon chain. And then what we'll do is we can have the opposite, where the OH added from the top face and is now coming towards you. So the methyl group is away. And the Br would be coming away from you, and the hydrogen is coming towards you. Let's ignore this. If we look at my intermediate, consider what happens to the other substituents. The way I have it drawn, the water molecule will be trans to both the methyl bridge and the same side as the methyl and the hydrogen. Okay? So, when the water comes in to attack, alright, so I went through that mechanism. Okay, so we can continue forward to the epoxidation and hydroxylation of alkenes. Alright, so this is an epoxide. It's a 3-membered ring. With oxygen. What we can do is if we treat an alkene with what's called a peracid, we can make an epoxide. Right? We can think of this epoxide in the same context of our bridged intermediates. Okay? What we can then do is treat our epoxide with aqueous acid to give a diol. Now, this diol will result from anti-hydroxylation. So let's draw this out. Let's do a ring. So we treat a ring with a peracid. Okay. Your book talks about a peracid which is called MCPBA. So if I just draw the generic per acid, oops, I said generic, so let's make this R. Okay, that would be a generic per acid. The MCPBA that your book mentions is like this. We will get an epoxide. Okay, and there will be stereochemistry here, either wedges, okay, or dashes. And then when we treat with a little bit of water, let me do the whole mechanism out. Alright, so here is our epoxide. I'm not going to make you be responsible for how this is formed. Now we have our epoxide. We add a little bit of acid. The first step is to protonate the oxygen. When we protonate this oxygen, we make the carbons more electrophilic. Okay, now water can come in and add. Okay, can't seem to move that up, so let's just deal with this. Okay, so when we have our epoxide, we add H+, and we protonate the oxygen. We will see this a lot in the spring. And when we protonate this oxygen, we make the carbons more electrophilic. There's a greater positive charge now, partial positive, on these carbons. And so water can attack and break the epoxide. We have anti-attack. We make an oxonium ion and deprotonate and get our trans diol. We can also make dihydroxylated products or glycols by reacting osmium tetroxide. We're not going to do it in pyridine solution. This reaction proceeds with syn stereoselectivity. So the non-green way, okay, this reaction is just not very green to begin with. Osmium is toxic and expensive. Okay. Non-green used to use osmium tetroxide, so OSO4 in sodium bisulfite or sodium sulfite in water. And so if we treated our alkene with osmium tetroxide, we would get a cis diol. Now what we can do is we can use a solvent called NMO, or we can use tertiary butyl hydrogen peroxide. So NMO looks like this. And tertiary butyl hydrogen peroxide looks like this. And this allows for a catalytic amount of OSO4. So this is a lot greener. Regardless, the product is a cis-diol. We can also oxidatively cleave alkenes, and this will give us carbonyl compounds. We're looking at the formation of ketones and aldehydes. The reaction is going to be called ozonolysis. Alright, so what we have is our alkene. We add ozone, and then we can add zinc in water, or DMS, which is dimethyl sulfide, like this. What this will do is result in the cleavage of this alkene, and you get a carbonyl at each position. Alright, so what I did was, you're going to put a carbonyl here and a carbonyl there. And because there are hydrogens attached, we get out two aldehydes. Right? Now, we're not going to worry about potassium permanganate. Okay? Before I move on, I just want to go back and say a couple of things. Up here where I did the ozonolysis, I can't scroll up because it will move all the text. Alright, where we did the osmium tetroxide. You add, let's see if I can scroll down. Yes, let's scroll down. Okay, let's cross this out because we're not going to do this. With the osmium reaction, first you add the osmium. Okay. You don't need to know this mechanism, but what this results in is the following. Intermediate. So you have this intermediate, and then you treat it with the mild reducing agent to get the diol. The net result is an oxidation because we added oxygen. With the ozonolysis reaction that we looked at, with the NMO or the tertiary butyl hydrogen peroxide, these are used as co-oxidants. So you would see something like this. And you would get the same product. But by using these co-oxidants, you can use less osmium tetroxide. With the ozonolysis reaction, okay, the first step is adding O3. What this will result in is the following intermediate. And then this is treated with the dimethyl sulfide or the zinc in water. And this is also a mild reducing agent. And it breaks it down so that we're going to break essentially like this. Okay, it's going to reduce this ozonide and break the ring, and let's just number the ring so we keep everything in order. One, two, three, 4, 5, 6. So we get this dialdehyde product. Okay. Again, we get an aldehyde because I have hydrogens here. The net result is an oxidation because we added oxygen. Okay, we're not going to worry about this. Proiodic acid. Alright, and so just to the reaction stereochemistry, you can look at these general rules and say that the formation of a new chiral center by reaction of achiral reactants results in a racemic mixture. Okay, and you can also say that the formation of a new chiral center by reaction of chiral products results in unequal amounts of distereomeric products. Really, what I would do, instead of memorizing these rules, just look at the reagents and know how they react. And we're not going to worry about synthesis. And so that will conclude Alkenes 3.